Hi folks, welcome back to Physics with Captain Rod. I'm making this to help you out with your homework. You folks in Physics 111, we're going to take a look up at Unit 2-1, numbers 9, 11, and 12. So let's rock on. Okay, so number 9 says something about a boat moving through water with two forces acting on it. So right there, when you read these, first thing you want to do is maybe draw a picture. All right, we have a boat. It's moving through water. Good enough. One is a 1650 Newton force pushed by the water on the propeller. So basically, all right, this thing's got a prop, not a, I should have read that a little further. We got a boat motor. And what they're saying is that there's a forward force pushing on the propeller. So this right here is some number given in the problem. Mine says 1650, but you probably have a different number. Then it says there's an 1100 Newton resistive force due to the water around the bow. So basically what they're saying is the bow is plowing through water, and that's creating a resistance on the bow. We could call it maybe, how about R for resistance force? How's that? Now, there's also vertical forces acting on the boat. There's what we call a buoyancy force acting up. That's what keeps the boat afloat and the weight of the boat down. But they're not relevant in this question here. This is a one-dimensional problem. And that's pretty well it. So now you're going to write a Newton's second law equation. Now that's going to be sum of all forces equals mass times acceleration. And remember, Captain Rod's rules of thumb, carrots here. Identify the acceleration direction if you can and call that positive. So the boat is going to accelerate to the right in my picture because this force is bigger than this one. Now, write your Newton's second law equation. I'm not going to do that for you. And then equals mass times acceleration. And that's going to allow you to find the acceleration of the boat. The big thing you have to get in the habit of is drawing these pictures on your own and getting in the habit of drawing the force vectors. Part B, if it starts from rest, how far will the boat move in 22.5 seconds? So part B is a study of purely motion. Now, when you study motion, you're studying the relationship between the position, which I'm going to call x here, or how we'll measure it, the velocity, which describes how this thing is changing, and the acceleration, which describes how this thing is changing. And the acceleration is what you just found. So start by drawing a graph of velocity against time. Boat probably starts from rest, so 0, 0. Now it says something about 22.5 seconds. So we got 22.5. I'm just going to put a t here, but that's a number given in the problem. We're going to have some sort of v final, or that's the velocity here, this distance, that's the velocity at that time. And you can calculate it from this. Acceleration's equal to delta v over delta t. This is what you found in the first part. This was given in the problem. Calculate this, your change in velocity, and that's going to tell you this on the graph. Then we'll make a constant acceleration assumption and move on. And keep in mind that these graphs have two important properties, slope and area, and that should get you through that problem. So I'm going to call that enough with number 9. That's plenty of detail for number 9. Let's chat about 11. Okay, let's see. After falling from rest from a height of 25 meters, a 0.55 kilogram ball rebounds upward, reaching a height of 15 meters. If the contact between the ball and the ground is 2.4 milliseconds, what is the average force exerted on the ball? Okay, so this one's got quite a bit going on. I'm going to give you directions for now. However, we'll probably come back and revisit this problem here in a few days because we're going to start talking about principles of work and energy. But the ball starts here at what I'm going to call position 1. It says 25 meters high or something like that. And it falls and accelerates down. Here's a picture of the ball right before impact. It's going to be moving down at some speed. I would call that V2 because it's the velocity in picture 2. Now the ball's going to hit the ground in reverse direction. I'm going to move over here now. I don't mean that the ball's physically moving to the right here. This is time 3, and it's in theory right here, but later in time, and it'd be just too muddled in the picture to put it right there, so I'm going to move it over. This is right after it leaves the ground. It's going to be moving up now with some sort of speed here. We should call that like V3. And it reaches a height of 15 meters. So it ends up here. Keep in mind it's going to slow down. Right? And let's call this position 4. Now, the mass of the ball also given in the problem. So remember what I always say. A picture is worth 1,000 words. Well, and I like to say in physics, it's 2,000. Okay, so really focus on your pictures. And an important thing to realize about this problem, there's 4 kind of important times to consider. All right, where the ball started, what it was doing just before impact with the ground, an instant after it leaves contact with the ground, and its highest point. Okay, these are all going to be kind of important. Now, let's talk about position. What's happening from 1 to 2? Draw a velocity graph. And you know, if you want to just do down positive, it'd be perfectly fine. That graph is going to look something like this. What you're given is the displacement here. I'm going to call that a delta x. That's given in the problem. Figure out how to use this graph to get this. That's your velocity 2, that velocity right there. Okay, that's what we did the first 3 weeks of this class kind of thing. Okay, next. Let's deal with 3 to 4 next. So in picture 3, the velocity is some positive number that we don't know. We'll call that V3. And in picture 4, the velocity is 0. Okay. The time here, we don't know, just like we didn't know before. But what we do know is the distance, the height. Okay. So use this graph and the fact that you know the distance to find the V3. So in this graph, you're finding V2, and in the other graph, you're finding V3. Okay. Now we're going to talk about what's happening between 2 and 3. So when the ball hits the ground, I'm going to draw a picture of that right here. You know, there's going to be this time when the ball's kind of deformed, this contact time, and the ground is going to put a pretty decent upward force up on that ball. I'm gonna, I'll just put F. You know, if you don't believe it, you know, imagine you had your finger in here, what would happen? You know, depending on how hard that ball is, you might break it, right? That force interaction between the ball and the ground can be pretty considerable. Now, also, there's a gravitational force. I suspect you can just ignore the gravitational force because it's probably not going to be significant in this problem. And here's some evidence of that. You know, again, picture a rock around the mass that they mention here, which is, if we're to go here, 911.5 kilograms, which is right around a pound. Okay, so imagine that this rock, and here's your fingers, and here's the ground, and it's just sitting there. That's no problem. You won't have any issue with that at all. However, if the rock was dropped from 20 meters high, and lands on your fingers when they're laying on the ground, you'll probably bust them. So the moral of that story, that force interaction between the rock and the ground is very large compared to the weight of that rock. So getting back to our free body of the rock, you can probably just ignore the weight of the rock. And that'll be the only force, right? And that force is going to equal mass times acceleration. And remember, your acceleration is change in v over change in t. You're going to get that from these things, your V3 and your V2. Keep in mind when you calculate them, one of them is up and one of them is down. Okay, so that's going to make this a fairly large change in velocity. If you have trouble with that, ask, and I'll help you work it out. So that's probably enough on number 11. That's pretty well almost worked out. Let's chat about number 12. Okay, so a 25 Newton force is applied in the positive x direction to a block. All right, so we've got a block with a 25 Newton force applied in the positive x direction. I'm just drawing what was given in the problem. Now, mine says 25, yours might say a different value. At rest on a frictionless surface. Now, other forces that are here, there's a gravitational force down equal to mg, right? Surface and contact, that's going to give us a normal up. Sometimes these are needed in the free body, sometimes not. You can never go wrong by putting them in there. If this were a test problem and you left them off, I probably wouldn't take any, no, not probably, I wouldn't take any points off because I don't believe they're going to be relevant. And if somebody left them in there, I wouldn't take any points off of theirs either, right? But, when you're dealing with friction or in other contexts, other problems, these forces can be important. So for right now, this problem, these two are optional in the free body. I wouldn't give anybody any crap if they put them in there. I wouldn't give anybody any crap if they left them out. Okay, part A. Find the acceleration. So that's just a Newton's second law question. Sum of all forces equals mass times acceleration. You're going to get these from your free body. It should be really, really self-explanatory. Mass given in the problem, find the acceleration. Almost nothing to that. Part B, how fast is it going after 4 seconds? Right, so what I'd like to see doing is, that's a motion question. So draw a velocity graph like we always do for any question about motion. Velocity against time. And I'm not going to sketch this one. I've drawn too many today, but I'm almost certainly this block is starting from rest. Oh yeah, it says starts from rest. Okay, and then how fast is it going after 4 seconds? So you come over here, 1, 2, 3, 4. You don't know the how fast, but you have to push forward. Put a dot on that graph, okay, and then label it. And then again, concepts of slope and area will get that question answered. So that's probably enough to get that one done. I hope that these help you with your homework. Have a great day.